Hello, in this video I'd like to complete the test review for Calculus 1, test number 2. We've got two sections, a no calculator and a calculator permitted section that we'll be completing on Friday the 16th. And the problems that you'll encounter on the test will be very similar to what you see here. Feel free to skip around in this video and pay close attention to those problems that may seem confusing to you. And if you've got further questions before Friday the 16th, please reach out to me and let me know. So on the no calculator portion, you'll be asked to differentiate several equations, and it'll be your responsibility to decide which technique seems to work the best. So in problem number 1, if we're looking for the derivative of f, it looks to me like we've got two separate terms, and I can just use the power rule and the linear rule for each. So without a whole lot of work being shown, we can identify what the derivative function is. The first derivative function is 4x cubed minus 4/3. For a problem like number 2, I recognize that there's a product of two functions, so I would use the product rule here rather than distributing. If you choose to distribute on the test, that would be fine. Just make sure that you show all of your work for the process that you've chosen. For me, I'm going to use the product rule, and I know that I need to take the derivative of the first function, which is negative 20x to the 4th power, times the second function, plus the first function times the derivative of the second. And even though we can simplify further from here, I'm going to ask that you not simplify for this test, and instead this would be our final answer. So certainly you can see my opinion, or you can recognize my opinion, that the product rule is superior in this case. Rather than taking the time to distribute and then apply the power rule repeatedly, I'd rather use the product rule and stop here at this point to save ourselves some time on the algebra, and also to reduce the likelihood of making a mistake on the algebra steps to simplify. For a problem like number 3, I see that we would need the quotient rule here. And you may notice my derivative notation, I'm switching back and forth between Leibniz and Lagrange. Typically when I see a problem originally written in function notation, I'll use Lagrange notation. And if I see an equation written in traditional y equals notation, then I'll use Leibniz notation for my derivative. So for this particular example, we need the low function times the derivative of the high function minus the high function times the derivative of the low, and all of that divided by low, or low squared. And again, since this is a test on your knowledge of the calculus process, we can stop here. This is not a test over your understanding of algebraic simplification, so I'm okay with you stopping with that result. With a problem like number 4, I see an inner function and an outer function. So because of the inner and outer function composition, I think the chain rule would be appropriate here. And the chain rule says that we take the derivative of the outside function, and we leave the inside function alone for the time being. Then we immediately multiply by the derivative of the inner function. Simplification here isn't too challenging, but again, it's fine if you want to stop at this point. In fact, this is the solution that I would be looking for this question on the test. You don't have to simplify using algebra. For number 5, we've got y equals sine of x cubed. Remember the implied grouping symbol that should be here around the trig function. So again, we have a function inside of another function. I'm going to treat this like the chain rule. And the derivative of the outer function, and we keep the inside function as it is for the time being. Then we immediately multiply by the derivative of the inside function, and now we've executed the chain rule. For problem number 6, even though this is a trig function that we don't see all that often, this is one of the derivative rules that you should have memorized. The derivative of secant of x is equal to secant of x times tangent of x. So with that in mind, and we recognize this being a chain rule on the account of the inner function and an outer function, we'll state that the derivative of secant of 2x squared would be secant of something times tangent of something. The something happens to be the inner function, untouched, so we do use that 2x squared both times. And because this is a chain rule and we've identified the derivative of the outer function, we need to multiply this by the derivative of our inner function. You could include a grouping symbol here, although it's not necessary. That grouping symbol would be a nice way to capture the derivative of the outer function, and we know that that derivative must be multiplied by the derivative of the inner function. In any event, this would be a good answer since we're not simplifying any further using algebraic steps. With number 7 and 8, I'll still use the chain rule. It's pretty popular. It's a pretty popular rule to use in calculus class. So dy dx, the derivative of y with respect to x, would be the derivative of the outside function, keeping the inside function as it is, and then immediately multiplying by the derivative of the inside function. We, of course, could simplify a little bit further from here, but I'm not interested in that for this particular test. For number 8, dy dx, the derivative of y with respect to x would be the derivative of the outer function, which is the natural log of something. It's not actually x, but it's the 1 over the argument, which in this case is 4x cubed, 1 over the inside function, and we immediately multiply by the derivative of the inside function. You should be careful with this and recognize that there is a domain restriction. The derivative of natural log of x is only 1 over x when x is positive. So in this case, we are assuming that 4x cubed is also positive. If that were not true, and this is kind of a description of our domain, if this were not true, if 4x cubed produced a negative number, then it could not be used as an input to the natural log function. We don't really have to identify the domain in this type of problem when we're just practicing with derivative rules, but it is good to keep in the back of your mind that to recognize that there are domain restrictions. For the next collection of problems, we need to find the equation of the tangent line at a particular point, and we should report our answer in slope-intercept form. So let's recall that the derivative function is going to be very important to find the slope of the tangent line. So the derivative function in this case is 3x squared minus 4x. And if we evaluate this derivative at the supplied x value, 3 times 2 squared minus 4 times 2, we will obtain the slope of the tangent line. So again, this is done without a calculator, so 2 squared is 4, and 4 times 3 is 12. 4 times 2 is 8, so it looks like our slope is 4. And maybe we can make a note of this here. Our slope is going to be 4, and then when we use our our point slope formula, we've got y minus 0. I'll keep these separated like the 3 parts that we've completed. Y minus 0 is equal to the slope 4 times x minus 2. So y is equal to 4x minus 8. And since the calculator is not permitted, we can't really check our work visually, but while you're practicing at home, I think that would be a good idea. Go ahead and plot this original function and plot this tangent line function, and we want to see if the graphs intersect at this point and if this linear function does produce, or does it appear to produce, a tangent line. Now, number 10 is done much the same way. It's going to be a little bit more challenging on account of the quotient rule being needed for the derivative. So here we go, and I'm gonna treat this negative sign as the negative sign up here. Remember, a negative sign in front of a fraction can go to either the numerator or the denominator, but it does not go to both. And while I'm using the quotient rule, I'm going to treat it like the negative sign is in the top. So we've got the low function times the derivative of the high function minus the high function times the derivative of the low function, all divided by low, or low squared. Since we're going to be using this function in a minute, I do think that it would be beneficial to simplify. So I will distribute this negative 4. We've got a negative 4x squared minus 16. I'll distribute this minus sign to make this negative 4x a positive 4x, and that positive 4x times 2x is 8x squared. The denominator I'm not going to FOIL. I'm not going to distribute that pair of binomials. I'll leave this one as it is. And in the numerator, it looks like we've got 4x squared minus 16 over x squared plus 4 quantity squared. So there's our derivative rule. And now we would evaluate our derivative rule at an x value of 0, as indicated by the point supplied to us. So we need 4 times 0 squared minus 16 over 0 squared plus 4 quantity squared. In the numerator, that's 0 minus 16, so negative 16. And in the denominator, we've got 0 plus 4, which is 4, and 4 squared is also 16. It looks like our slope comes out to be negative 1. Now, we know that the slope is negative 1, and we've got a y value of 0 and an x value of 0. So as we simplify this equation, we've got the tangent line that will appear at y equals negative x. So here again, we won't have a calculator on the test to verify our work, but while you're practicing at home, I think it would be a good idea. Graph our tangent line function, graph our original function, and we'll see if this tangent line does strike the original function at this point. For numbers 11 and 12, we have to use implicit differentiation to find dy dx. And on the test, I think I'll give you a picture of each of these graphs, because you don't have a calculator available to you to create one on your own. I'll give you a picture of each of those graphs so that when you obtain your derivative, you could verify if the derivative function seems to match what the slope at a particular point might be. In fact, for the test, now that I'm saying that out loud, I think I want you to find an equation of a tangent line. Find an equation of a tangent line at a point. And I'll provide a point as well as the implicit equation. So you'll have something like this. And in this case, I could probably supply you with the coordinate 16, 5, and we would find the tangent line at that particular point. So let's talk about the implicit differentiation here. Remember, we're applying the derivative rule to both sides of the equation. And the derivative of the constant, of course, is 0. The derivative of 5x, since this variable matches the differentiation variable, we can just use our regular rules here. For the derivative of negative 3y squared, well, I like negative 6y, but remember, since this variable differs from the variable of differentiation, this dx, we've got to turn around and multiply by the dy dx differential. With a little bit of work, we can isolate the dy dx. You may not have to show every step because a lot of this is pretty straightforward. But we're going to subtract 5 and then divide by negative 6. Those two negatives will cancel in the process of division. So we've got dy dx equal to 5 over 6y. That would be the solution to this practice quiz, but since I do want the tangent line at this particular point, let's go ahead and figure that out. Well, the slope would be 5 over 6 times the y-coordinate, which the y-coordinate is 5, and it looks like the slope is 1/6. And since I'll provide you with an image of the graph, it'll be similar to this. Here's an image of that graph. Here's the coordinate, 16, 5. You'd be able to draw that by hand. And we think that the slope might be 1/6. So that seems pretty reasonable. Let's go ahead and finish this out. If the slope is 1/6 and we've got our point slope formula, y minus 5 equals 1/6 times x minus 16, well, that leaves us with y minus 5 equals 1/6 x minus 16 sixths. I'll simplify in just a moment. We'll add 80 sixteenths to both sides because that's going to be a common denominator. The 16 would be a common denominator. So maybe it would have been easier to simplify this first. That'll be a little bit difficult to do without a calculator, finding your common denominator in a short amount of time. But we know that we're left with 1/6 x and then negative 16 plus 80. That leaves us with 64 sixteenths. And 64 is divisible by 16. So we have y equals 1/6 x plus 4. And that appears to be our linear equation of our tangent line. So we can check that. Y equals 1/6 x plus 4. And clearly I made a mistake, so let's see if we can figure out what went wrong. Whoops, I don't know what I was thinking back here. The common denominator is 6, not 16. I think that might have thrown us off just a little bit. So 5 is 30/6, and so we're adding 30/6 to both sides of the equation. That's going to leave us with 1/6 x plus 14/6 and 1/6 x plus, this looks like 7/3 to me. Let's see if that's any better. So instead of a y-intercept of 4, we're going to use a y-intercept of 7/3. And there we go. That's a little bit better. So let's see if we scale this a little bit differently. Certainly, this no longer looks like a scale or a slope of 1/6, but I've adjusted the horizontal and vertical axes. And it does, to me, look like a point of tangency now. So I think we've done much better there. Hopefully you don't make the same mistake as me on your test, but also since we're providing you, or I will provide you with a graph for a problem like this, then you should be able to troubleshoot any problems you might have. Now this equation here is a bad example for finding a point of tangency because there aren't a whole lot of whole number points that show up on this graph. So we'll ignore that portion for right now. We'll just use this as a chance to practice our implicit differentiation. So since we're deriving, or we're finding the derivative with respect to x, the first thing we must do is apply the differential to both sides of the equation. So the derivative of 2x cubed in terms of x is simply 6x squared. And on the right, we've got negative 10y times dy dx. That differential again is included because the variable disagrees. The derivative of negative 2y is negative 2, but again, we've got to include this differential, dy dx, because this variable differs from the variable of differentiation. And the derivative of 2, well, there is no variable here, so we can apply the constant derivative rule. That becomes 0. You've seen this trick already, that when there are multiple differentials available, we'll treat that like a common variable, dy dx, and factor out a negative 10y and a negative 2. And all of that is still equal to 6x squared. Now when we isolate dy dx, we'll have 6x squared divided by negative 10y minus 2. And of course, if I had a coordinate, some x and y coordinate, x1 and y1, we can now apply the differential using the x1 and the y1 values to find the slope of the line, and then our point slope formula to report our tangent line at that specific point. And so that about does it for the no calculator portion of the test number 2 that you'll see on the 16th. And as far as the outline for the test goes, on the no calculator portion, you'll see 6 derivative questions about polynomials, power, exponential, and logarithms. So basically the derivative rules that you've memorized. You'll see 6 questions on them, and I'll ask you to choose 4 to complete. There will be 6 questions on the product, quotient, and chain rule. Again, you'll see 6 problems, but I'll ask you to choose 4 to complete. And then finally, for the implicit differentiation that we were just practicing, I'll have 2 implicit differentiation questions where you have to identify the tangent line equation, and I'll have you choose 1 of those. So I think rather than asking these questions again on this test where you find the slope of a function, or the equation of the tangent line of a function, I think I'll just do that. I'll ask those questions in the midst of a implicit differentiation problem. So that's what your no-calc test is going to look like. I'm going to prepare another video to go through the calculator permitted portion of the test, and please make sure that you watch that to see some practice problems as well as the outline for that test as well. Thanks for watching.